Hi. So this is 2.4, chain rule. So I'm going to start with an example that I hope you can do without any issues here. The derivative of x squared, of course, is just 2x. So I hope you knew that. That's just the ordinary power rule. But now I want to take the derivative of something a little more complicated. How about sine squared of x? And when we write sine squared, I hope you realize that you're squaring sine of x, right? So this is the derivative of sine of x, the whole thing squared. Right. So how could we do this? Well, you might think that it's the power rule. You just bring the 2 in front and multiply by sine of x. But that can't be it, right? For one thing, hopefully that you remember this, that the derivative of sine by itself, right, without the square, is cosine. So why would it be that if you take the derivative of sine of x squared that you don't get a cosine, right? So that doesn't seem to make sense here. Okay. So rather than try to use the power rule, here's the way I would suggest. When you square something, right, x squared, of course, is just x times x. And so sine of x squared, or sine squared of x, same thing, is just sine of x times sine of x. So why don't we take the derivative of sine of x times sine of x? So, right, same thing as sine of x squared. So how are we going to do it? How are we going to do this? Well, using the product rule, right? So now it's a product, sine times sine, where u, or f of x, right, is sine, and v, or g of x, is also sine. They don't have to be different functions. They can be the same function. The product rule still applies. So using the product rule, we do the first times the derivative of the second. And I know we should be able to do this in our head. Derivative of sine is cosine, right? Plus second, the second is also sine, times the derivative of the first. And of course, the derivative of sine is cosine, so we get sine times cosine plus sine times cosine. So, right, we have 2 of these, right? 1 sine cosine plus 1 sine cosine is 2 sine cosine, sine times cosine. And so that should be the answer. And now you can see the issue with the way we did it here. If you just use the power rule, bring the 2 in front, you get 2 times sine, but what you're missing here is the cosine. Try to erase that. And let me erase the red x here. Right. So yep, so now we know the answer is not 2 times sine, but 2 times sine times cosine. Okay. And that makes sense because, again, the derivative of sine is cosine. If you're taking the derivative of sine of x squared, there should be a cosine as a factor of the answer here, right? So, yeah, so we did it by using the product rule. Now how do we go back and use the power rule when you're not just taking the derivative of x squared, but the derivative of sine of x squared? Right, so that's where the chain rule comes in. Okay, so the chain rule in general goes like this. Right, so the idea is you're chaining 2 functions together. You're taking one after the other. Right, so you're taking a function of another function, right? And some books like to write this, the composition of 2 functions, as f composed with g of x. Our book doesn't do that very much. Our book prefers to write it this way, right? So our goal is to find the derivative of y with respect to x. And the way to think of it is you're taking the derivative of f, but applying it not to x, you're applying that to g of x. And then you have to multiply by the derivative of the inside function, g. Right? And so that's one version of the chain rule. Okay, so this is the chain rule, so version 1. And then there's another way to write it. If, let's say, oops, I didn't mean to use red. Let's say we let u be the inside function, which is g of x, right? Then the derivative of u is just g prime of x, right? So in that case, we can write the derivative of y with respect to x as the derivative of f. Remember, y is equal to f, so it's just the derivative of y, but not with respect to x. It's with respect to g of x, or with respect to u. Times the derivative of g is just the derivative of u. So this is also the chain rule, using variables, so version 2. And in looking at version 2, it looks an awful lot like we can just cancel the du's here, and you get dy over dx. So, I mean, I guess you can think of it that way, but it's not quite what's going on here, right? You're just thinking of this factor here as dy over du, and then this factor g prime of x as du divided by dx. Okay. Right. So, back to our example. Y is equal to the sine of x squared. And we want to find the derivative of y with respect to x. Okay. So the way I would think of this is the outside function is the squaring function. So you can think of your f of x, right, which is your y, as just x squared. Right. Now, where's the sine of x? That's the inside function, right? So that's our u, or g of x. Right. So we're squaring not x, but we're squaring sine of x, right? So if we put these together, if we take f of g of x, right, we're taking g of x and squaring it, because that's what f does to x. It squares it. What does it do to g of x? It squares it. Same thing. And now what's g of x? G of x was right here, sine of x. Right. Right. And again, we could write this as sine squared of x, not to be confused with the sine of x squared. Right. We don't see this too often, but it could come up later. But yeah, so we're not squaring the x, we're squaring the sine of x. Okay, so now we just apply the chain rule, right? If we take f prime of x, well, the derivative of x squared is just 2x, right? But notice in the chain rule, we need f prime of g of x. So that's just 2 times g of x. But g of x was sine x. Right? So we get 2 times sine x. And if you remember, that was our original guess. Well, I erased it now, but that was our original guess, and it was wrong. So what's wrong, of course, is that we're missing the second factor here. Don't forget to take g prime of x. Right? So, yeah, what's g prime of x? What's the derivative of u with respect to x? Well, it's the derivative of sine, which of course is cosine. And so that factor goes at the end here. That's the g prime of x, or the right, du over dx. Right? And then that's the correct answer, which we got by using the product rule up here. So same thing. And incidentally, there's another way to write this. You could write this as the sine of 2x. So I would accept that too, of course. Right. And if you don't know why that is, look up in the front cover of your book something called the double angle formula. So this is a trigonometric identity that you can write sine of 2x as 2 sine x cosine x. And so you can also go backwards. You can take 2 sine x cosine x and just write it as the sine of 2x. But again, I will not be picky about that. You can write it either way. It's fine with me. So again, ideally, you should remember the double angle formula from pre-calculus or trigonometry. On the other hand, if it comes up, I will remind you of it and where to find it in the book. It's at the very beginning. I think it's also in chapter P, I think section 3, where they talk about trigonometry. So, yep, little known fact about sine of 2x can be written as 2 sine x cosine x. It comes in handy in some cases. Here we didn't really need it. Like I say, I would have accepted this version here, but either way is fine. Okay, so that's how the chain rule works. Let's look at some other examples here. So I guess I'll call this example 2. Suppose y is equal to, let's do the square root of x cubed minus 5x squared. And we just want to find the derivative. Right? So it seems simple enough. It seems like we should have been able to do this before with just the sum rule and product rule, or quotient rule, or difference rule, power rule, whatever, right? But here's the problem, right? We can rewrite this square root as raising the whole thing to the power 1/2, right? So I'm hoping you remember that the square root of x is also x to the 1/2. So yeah, we can use the power rule here. However, remember that we're not taking the derivative of x to the 1/2. We're taking the derivative of x cubed minus 5x squared to the 1/2, right? So it's a function of another function, right? And I would think of this inside the parentheses as my g of x, right? Or if you prefer, u, right? So that's going to be the x cubed minus 5x squared. Okay. So, using the chain rule, you take the derivative in the following way, right? You use the power rule. So, we did this already, I think a long time ago. The derivative of x to the 1/2 is 1/2 times x to the negative 1/2. So what would it be for this function here? Well, you still bring the 1/2 in front, and you multiply by x cubed minus 5x squared, and you still raise that to the power negative 1/2. But now, we're not done. We have to multiply by the derivative of g of x. So we multiply by the derivative of x cubed minus 5x squared, and so we still have to take this derivative here. Okay, everything else here, right, we already took the derivative here, so this can be left alone, at least for now. So just rewrite it. Same power, negative 1/2. And now what's the derivative of x cubed minus 5x squared? Of course, right? Power rule, difference rule, constant times function rule. So this is just 3x squared minus 10x. Right. You don't have to go step by step there anymore, I hope. But then that's the answer, right? So now we're done. Now, we could either leave it like this. Typically, I would bring this factor in front. So I would just switch the factors here. And then x cubed minus 5x squared to the power negative 1/2. And I don't think there's a whole lot else we could do. Oh, we could factor out an x here, right? Shoot, I didn't miss that. And yeah, actually we could factor out an x here too, but it doesn't look like it. But it's a sloppy x. All right, so let's try that. Let's leave it as it is here. And I would accept this too. But remember, it was originally written with a radical, so we can also do it that way too, right? So this is going to be x times 3x minus 10 over 2, right? So the 2 is in the denominator. And then all of this, because the exponent is negative 1/2, it's going to be in the denominator. And the 1/2 becomes the square root, right? Okay. Again, I would accept this as well, except there's one more thing we can do. We could factor out the square root of x squared here. And that'll allow us to cancel the x's. Right? So yeah, x divided by x is 1. So these cancel. And so this is probably the best way to write it. 3x minus 10 all over 2 times the square root of x minus 5. So let me double highlight this because this is probably the best way to write it here. Right. So we simplified it by just, factoring out the x's, or in this case, the x squared. If you're wondering, wait a minute, wasn't this x squared here? I know some of you are thinking this. If you factor out x squared, how did it become an x? Well, I split it up as the square root of x squared times the square root of x minus 5. And the square root of x squared is, technically it's the absolute value of x. I guess we're going to assume that x is positive here. So this is x times the square root of x minus 5. So the square root of x squared became x. And that's where this x came from. It wasn't, right, it was x squared underneath the square root, but it's x outside the square root. Okay, so yeah, a very typical example where you would use the chain rule. Right? Let's do another quick one. So example 3. Suppose I'll just call it f of x, right? Because sometimes they'll be written this way. So let's just do x squared minus 5 to the power 12. To the whole thing to the power 12. And we want to find the derivative of f prime of x. Okay. So what could we do? Well, we could multiply this out 12 times. I don't think I would want to do that. I mean, there's 4 of them, right? Keep going until you write down all 12. I don't know why that became a 4. That's a 5. Yeah. Not the way you want to do it, right? You would essentially just either multiply it out 12 times or use the product rule 12 times. So no, we don't want to do that. At least I don't want to do it that way. Right. So yeah, right, we could do this without the chain rule. And maybe if this were just, x squared minus 5 squared, then this would be a reasonable way to do it. Just expand this out or use the product rule. But when the exponent is, say, 12, no thank you. I'd rather just use the chain rule here, right? And in fact, let's write down the chain rule for powers. Because this is the one you're going to use probably the most often. right? And it just goes like this, right? Suppose you're taking the derivative of some function, I'll call it g of x, to the power n. Right, here n is 12, but, in other problems n could be 2 or 3, or even, 1/2 for square roots. So, right, so we apply the power rule. This is n times g of x to the power n minus 1, but then the chain rule says multiply by the derivative of g. Okay, so that's the chain rule applied just to powers. Okay, and so we can use that here, right? If we want to find the derivative of f, well, we use the power rule, right? We bring the 12 in front, multiply by x squared minus 5 to the power 12 minus 1, which is 11. But then we're not done, right? We need this g prime of x. So we still have to take the derivative of what's g here. G is what's inside. So we need the derivative of x squared minus 5. Right. So what's the derivative of x squared minus 5? Of course, 2x minus 0, or just 2x. Right, and that's it. Again, this factor of 2x, I would tend to bring that in front and multiply by 12. So 12 times 2x would be 24x. And then don't forget the x squared minus 5 to the power 11. And then that's the answer for, 24x times x squared minus 5 to the 11th power. It's probably the best way to write it. Right. Okay, so very useful. Not completely necessary here because we did have this other alternative way to do it. But I would imagine if we did it that way, it would have taken hours to multiply it out or to use the product rule 12 times. Actually 11 times, but who's counting? Yeah, so the chain rule here is much more powerful, right? Right. So here's another one we can do. Suppose y is equal to, let's do the cube root of tangent x. Right. Find the derivative. Okay. I'm out of space here, so hang on, let me start over. Okay. So, yep, y is the cube root of tangent x, and we want the derivative. Right. And so we can use the same power rule as long as you recognize that the cube root of tangent x is just tangent of x to the power 1/3. And I know I just erased the power rule. We're taking the derivative of a function of x to the nth power. So that's n times g of x to the n minus 1 times the derivative of g. Right? So, yep. So for the derivative, well, n is 1/3 here, so this will be 1/3 times g of x, which is just tangent of x, right? Don't take the derivative yet, right? This g of x inside here is not g prime of x. The g prime of x is on the outside, not on the inside, right? And then what's 1/3 minus 1? I think it's negative 2/3. And then here's the chain rule part. We need to multiply by the derivative of g, the derivative of tangent. And we did that last time, right? So the derivative of tangent, hopefully you remember, is secant squared. So putting this all together, right, the derivative of y is just going to be 1/3 times the tangent of x to the negative 2/3 times secant squared of x. And you can leave it like that. If you prefer, you can rewrite this in terms of a radical. So the secant squared, I'll leave that on top. And then in the denominator, we have the 3 from the 1/3. And then we have the cube root of tangent squared of x. So you can write it that way as well. And, you know, there's other ways you can do this. You can simplify secant as 1 over cosine and tangent as sine over cosine, but not really necessary here. Okay. Right. So now let's do one where we can't use, right, the general power rule. So this is the power rule with the chain rule. So power rule with the chain rule. So here's something we can't do like that. Suppose y is equal to, let's do the cosecant, not of x, but the cosecant of 4x plus 7. Right. And again, we want to find the derivative. Okay. So, so just to remind you, well, hopefully you know it, but if not, here it is again. What's the derivative of cosecant of x? It's negative cosecant times cotangent. So that's good to know. Right. And you can do it by the quotient rule by doing 1 over sine x and then applying the quotient rule to that. Right. So that's one way to get this. So here's the issue, right? What we have is not cosecant of x, but it's the cosecant of some function of x. You can call it g of x if you like. I prefer just to call it u. So what's the derivative of y with respect to x? It'll be negative cosecant of u times the cotangent of u. And then the chain rule says multiply by the derivative of u. Okay. And we can apply the chain rule here, but we're taking the derivative with respect to x. And this, since this is cosecant of x, the chain rule says we multiply by the derivative of x with respect to x. But of course, this is just 1. So here it's not necessary to use the chain rule, but that's only because this was just x. If it's not x, if it's some function of x, then you need the chain rule here, right? So let's see how this works, right? So the derivative of cosecant is negative cosecant of u. U is still 4x plus 7. And then times cotangent of u, which is still 4x plus 7. And then the all-important derivative of u. So what's the derivative of 4x plus 7? Yeah, 4 plus 0. Right? It's just 4. Right. So this is negative cosecant of 4x plus 7 times the cotangent of 4x plus 7 times 4. But because it's just a 4, I would bring that in front and write this as negative 4 times the cosecant of, same thing, 4x plus 7 times the cotangent of 4x plus 7. And that we can leave that alone. Right. So that's the derivative of cosecant of 4x plus 7. And so the point is, for all the trig functions, the derivatives of all the trig functions that we learned, for example, we learned that the derivative of sine x was cosine of x. But if you'd like, instead of memorizing that, you might memorize the chain rule version. If you want to take the derivative of sine of u with respect to x, that's going to be the cosine of u times the derivative of u, right? So for every one of these rules that we learned last time, we also have the corresponding chain rule version of those. And the chain rule just has this extra factor of the derivative of u, right? So here's the one for tangent, which, yeah, we didn't use this one. We used the cosecant one, but this is secant squared of u times the derivative of u. So it's the same rules, right? We're not really doing anything different here other than changing the variable here from x to a u. Right? Or you can use y or w or some other letter other than x. But typically we're going to use u here, right? So all these rules have the corresponding chain rule. Okay. So yeah, again, the chain rule just takes getting used to. So let's do a slightly harder one. I think we're up to example 6. So how about, let's do f of x is equal to cosine squared of x cubed. Okay, so cosine squared of x cubed. Again, find the derivative, right? What's f prime of x equal to? Well, before we take the derivative, let's rewrite this in a more familiar way. What are we squaring here? We're not squaring, well, yeah, we are squaring cosine, right? We're squaring the whole thing. We're taking the cosine of x cubed, and then we're squaring that. Okay, so that's maybe a better way to write this before we take the derivative, right? So what are we taking the derivative of? Something squared. Right? So if you remember, the derivative of x squared is just 2x. So the derivative of this whole thing squared is just 2 times that whole thing, cosine of x cubed. Right? To the power 2 minus 1, which of course is just 1. And I would not write the 1 because in my mind this almost looks like a prime, which means you take the derivative again, and you don't want to do that, right? Okay, but we're not done because we still have to take the derivative of what's inside. So we have to take the derivative of cosine of x cubed. So again, this is the g prime of x, right? That's the chain rule part. Okay, so let's do that on the next step. Leave everything else alone, right? So 2 times cosine of x cubed, that stays. And now what's the derivative of cosine of x cubed? Well, the derivative of cosine is negative sine of x cubed. Right? Derivative of, I just wrote it up here, derivative of cosine, right, is negative sine. But notice that it's not cosine of x, it's the cosine of x cubed. So even here now, this x cubed, that's my u, right? That's my new g of x. So you see, we're not done yet, right? We still have to multiply by the derivative of the g of x, or the u. In this case, we have to multiply by the derivative of x cubed. So this is a chain rule and then another chain rule, right? So we're applying the chain rule twice. Let me bring the negative in front here, right? Because it's a positive times a negative. So we'll just make this a negative 2 times cosine of x cubed times sine of x cubed. And now the derivative of x cubed, of course, is just 3x squared. And that can also come in front. So negative 2 times 3x squared is negative 6x squared times the cosine of x cubed times the sine of x cubed. And that's good enough. Right? And it doesn't matter if you want to switch the order, put the sine first and then the cosine, that's fine too. That really doesn't make any difference to me. Just some people like putting sine and then cosine, but it doesn't matter. If you're really clever, you might note that this is also a version of the double angle formula that we just did, right? So if this is 2 times 6, then this is going to be negative 3x squared times the sine of 2 times x cubed. But again, not really necessary, just an alternative way to write it. Okay, so yeah, so this was a tricky one because it was the chain rule twice. It was the chain rule for the original g of x was cosine of x cubed, and then after we did that, the new g of x was just x cubed itself. So yeah, what made this tricky is that it was a function of a function of a function. Right? In other words, well, we can think of this as y as a function of another function. And so now if you want to take the derivative with respect to x, well, you take the derivative of f with respect to g of h of x, and then multiply by the derivative of g with respect to h of x, and then multiply by the derivative of h. And so that's what we did here, kind of in stages, right? So that's what happens if you have a function of a function of a function, and you can do this for as many functions as you have here, right? Just be aware, and I hope you're not confused by this. This is not f times g, right? This is not a product, right? So don't get confused with f of x times g of x times h of x, right? This would require the product rule. But here we're not multiplying them, we're composing the functions. This is where we use the chain rule, when you have a function of another function, right? Got it? I hope that helps. Okay, so let's do another example. F of x is going to be tangent squared of x. And before we try to take the derivative, you might want to write that as tangent of x, the whole thing squared. Okay, and then we'll just take the derivative. But notice what the question is. It's not to find the first derivative. We want to find the second derivative, right? F double prime. So yeah, we have to essentially take two derivatives. But the way you do that is you take the first derivative first, worry about that first, and then don't forget to do it again and take the next derivative, the second derivative, right? Okay, and I don't remember if we did this one. I think we did one similar to this, but it's the power rule, right? So bring the 2 in front, multiply by tangent of x to the 1, and then by the chain rule, we have to multiply by the derivative of tangent. Okay, so again, don't forget the chain rule here, right? So we have 2 times tangent, and then what's the derivative of tangent? Hopefully you remember, it's just secant squared. Okay, so that's it. Well, that's the first derivative, right? But we're not done because now we want to do it again. Now we want to take the second derivative. So we want to take the derivative of the whole thing, 2 times tangent x times secant squared of x. Right. Now again, this almost looks like a triple product, right? It's the product of 3 things, the 2, the tangent, and then the secant squared. So you can think of it that way as a product rule applied twice. However, the 2 is just a constant, right? That can just come outside first. So this is 2 times the derivative of tangent of x times secant squared of x, which is really secant to the power 2. So the 2 will just stay on the outside. Right. Now what rule are we using? Right, so this is tangent times secant squared. Times is a product. We need the product rule. So, yep, If you're not careful, you might take the derivative of tangent times the derivative of secant squared, but that's not going to be correct. Okay, so you can see why I'm using a curly brace here, because this is not going to be easy, right? But let's write out the product rule. And I know we just did it, so let's write it out one more time. The derivative of u times v is u times the derivative of v plus v times the derivative of u, where in this case u is the tangent of x and v is secant squared. Okay. So applying the product rule, we have first times the derivative of the second plus second, which is secant squared, times the derivative of the first. And this is all going to be multiplied by 2 in the end. Right. I think at this point I can just use a bracket here. I didn't need the braces. That's fine. All right, so tangent is tangent. We can leave that alone. But what's the derivative of secant squared? So we use the power rule, right? So 2 times secant. But don't forget, this is my g of x. So this requires the chain rule again. So now we have to multiply by the derivative of secant. Right. And I prefer to do that on the next step. So I'm going to leave this as the derivative, which we still have to evaluate next time. Okay, plus, okay, secant of x squared. We can leave that alone. And then the derivative of tangent, well, that's just secant of x. Secant squared of x. Okay. Yeah, no chain rule here because it's just tangent of x, not tangent of, say, g of x, right? Okay, so we still have to take this derivative here, the derivative of secant. And I think we remember that, I hope. Oh, this 2 will come in front of the tangent here. Sorry. Yes. So the 2 can come in front. So 2 times tangent times secant. And then the derivative of secant is secant times tangent. Right. And that's it. So we have secant squared times secant squared. That's secant to the 4th power. Right, we'll distribute the 2 later here. But notice what I have in the first term here. I have tangent times tangent, so that'll be tangent squared. And then I have secant times secant, that'll be secant squared. So I'm going to get 2 times, it doesn't matter which one you put first. I was going to do tangent squared, secant squared, or secant squared times tangent squared. Right. And then plus secant to the 4th power. Right? And in fact, we can factor out a secant squared because there's 2 of them here, and there's 2 of them here too. And if you factor out 2 of them, you're still left with 2 left over here, right? So, I don't know, that looks pretty good. You can make a case for just leaving it like this. Or you can distribute, and in fact, we could have just distributed the 2 here. So this will be 4 times secant squared times tangent squared plus 2 times secant to the 4th. Yep, I'm not picky. Again, this way might be a little bit better because if you have to set this equal to 0, you can just set each factor equal to 0. Whereas if you do this, it might be a little bit of a pain to do that. So, but not a big deal. Either way, oops. Either way is correct. Okay. Yeah, again, just don't leave it like this because you do want to simplify. right? Yep. You don't want to leave, tangent times tangent. You want to write it as tangent squared, for example, right? Okay. Yeah, so that is the answer. Remember, that's the second derivative here. So all of this was f double prime of x. Right. So yeah, you can see taking the first derivative was really no big deal. It was just the chain rule here. But taking the second derivative, we needed the product rule and the chain rule. So that was not quite as pleasant. But you got to get used to that. Yeah, I guess maybe let's do one more. And again, they're not going to get much more difficult than that, but I lost track of what number this is. So I'm thinking this was 6, and then this will be number 7. Okay, so we have a mass on a spring, and it has position x, so it's going horizontally, I guess, right? 5 times sine of 4t plus 8 times cosine of 4t. And the position is in meters, and t is in seconds. Right, so part A, we want to find the velocity at time t is equal to pi over 3 seconds. So it's just a little bit bigger than 1 second. I don't remember exactly, 1.07 seconds or something. Doesn't matter, we'll use the exact pi over 3, right? And then we want to find the acceleration at time t equal the same time, pi over 3 seconds. So we have the position, right? That's given. And we want to find the velocity and the acceleration. Right. So this is exactly what we did last time. Right. To find the velocity, we need the derivative of the position, or if you prefer, x prime of t. Right. And so, yep, we're just going to take the derivative, again, with respect to t now, of 5 times the sine of 4t plus 8 times the cosine of 4t. Okay, so it's just a sum rule, right? And then the constant times function rule. So I'll write it this way, right? 5 times the derivative of sine of 4t plus 8 times the derivative of cosine of 4t. So I use the sum rule and the constant times function rule. But now we need the chain rule because it's not the sine of t, it's the sine of 4 times t. Right. So the derivative of sine is cosine, 4t, and then times the derivative of 4t is just 4. So the 4 here is because of the chain rule, right? And then the derivative of cosine is negative sine. Right? And again, we're taking the derivative of 4 times t, that's just 4. Okay. So why don't I bring the 4's in front? Right? So 5 times 4 is 20, and 8 times 4 is 32. Oh, I'll put parentheses just in case. Okay, so that's the velocity at any time t, right? And that's the instantaneous velocity. So now, if we plug in pi over 3, what do we get? 20 times the cosine of 4 pi over 3 minus 32 times the sine of, again, 4 pi over 3. So hopefully you remember where 4 pi over 3 is. This is pi over 3 is 60 degrees. 2 pi over 3, 3 pi over 3 is just pi. So 4 pi over 3, we are down here in quadrant 3. And if you remember, in quadrant 3, both sine and cosine are negative. Okay? And yeah, the reference angle is just pi over 3. So cosine of pi over 3 is 1/2. But because it's in quadrant 3, cosine of 4 pi over 3 will be negative 1/2. And sine of 4 pi over 3 will be negative square root of 3 over 2. So it looks like we're getting negative 10 plus 16 times the square root of 3, which I think is a positive number, right? 16 square root of 3 minus 10. And that'll be in meters per second. Yep, don't forget units. Meters per second. Okay. Again, that's the exact value, and I prefer leaving it as the exact value. If you'd rather approximate, again, for you engineers, you will approximate this with your calculator. So let's see if I can do that very quickly here. Minus 10. So I get approximately 17.7 meters per second. Right. And it's positive. Remember, this is velocity. Velocity can be positive or negative. All right. It turns out to be positive, so that means it's moving in the positive direction, presumably to the right. Right, and if the velocity were negative, it would be moving to the left, right, or down, depending on which way we're going. Okay, so that's only part A. Remember, we need part B as well. We need the acceleration. So if the velocity is the first derivative, the acceleration is the second derivative. So to get part B now, the acceleration, we need to take the second derivative of position. However, having taken the first derivative, v is the first derivative, we just have to take the first derivative of v. Right? So we already know what v is. It's this thing up here. So now we just take the derivative of that. In much the same way. Okay, so again, I'll do it the same way, right? So this is going to be 20 times the derivative of cosine of 4t, 4 times t, sorry, minus 32 times the derivative of the sine of 4 times t. Right. So the derivative of cosine is negative sine. And then don't forget the chain rule again. The derivative of 4t is 4. And the derivative of sine is cosine. And the derivative of 4t is again 4. Right. And you'll notice sometimes I put parentheses around the 4t and sometimes I don't. But it's just a personal preference. Okay, so for the next step, let's just bring the 4 in front here. 4 times negative 20 is negative 80, and 4 times negative 32 is negative 128, I think. So we're getting some bigger numbers here. Yep. Okay. So that's the second derivative. That's the acceleration, right? At any given time. We wanted this only for time, right, pi over 3. So now we plug in pi over 3, and I think I have just enough space to do that. So negative 80 times the sine of 4 pi over 3 minus 128 times the cosine of 4 pi over 3. So remember, sine of 4 pi over 3 was negative square root of 3 over 2. And the cosine of 4 pi over 3 is negative 1/2. So even though this looked like a negative minus another number, so it looked like it was going to be negative, it turns out that, right, a negative times a negative here will be positive. So this is going to be 40 times the square root of 3 plus 64. And that's the exact value. This will be in meters per second squared. Remember, it's an acceleration, so it's meters per second, or meters per second squared. And if you want the approximation, let's see, square root of 3 times 40 plus 64. I get 133.28. Oops. 33.28 positive, right, meters per second squared. And again, acceleration, right, can be positive or negative as well. Acceleration, right, if you're accelerating to the right, you're going faster and faster to the right. Oops. Right. However, don't get confused with acceleration and velocity. Right? I mean, obviously, acceleration is the rate of change of the velocity. But if one is positive, the other could be negative. Right? Your velocity could be positive in the sense that you're moving to the right. But if you're slowing down, if your velocity is decreasing, right, then your velocity is positive, but your acceleration would be negative. Why is your acceleration negative if you're moving to the right? Well, because you're moving to the right, but you're slowing down. In other words, you're being pushed this way. If you're slowing down, something is pushing on you to slow down. And that force is going to the left, in the negative direction. Okay? So your velocity can be positive, but your acceleration can be negative. Again, not in this case. In this case, they're both positive, right? So that means you're moving to the right and you're moving faster and faster. So you're being pushed to the right, which causes the velocity to go faster and faster and faster to the right. So again, we'll come back to this idea of when the first derivative can be positive or negative, and the second derivative can be independently positive or negative. So that will come in Chapter 3 when we talk more about applications. But in this case, I just wanted to use the chain rule to take the derivative here and also to take the second derivative. And so I hope that helps. And again, it does take getting used to the chain rule. It's very easy, for example, to forget the 4's here. The 4's just come from, right, the derivative of 4 times t. But I just did that in my head. The derivative of 4 times t is 4. Right? So, yeah, same thing over here too. Right? And this was for the second derivative. We had to do that for the first derivative as well. So where did these 4's come from? It came from taking the derivative of the 4t, right? And the chain rule demands that we do that. Okay, so I hope that helps. And that's the chain rule.